Today in the workshop, we're working with a multifunction sensor. You'll see how the LSM303AGR can be used to measure acceleration and magnetic fields. We'll also calibrate it for improved accuracy, and we'll build a compass with an OLED display. We're heading in the right direction today, so welcome to the workshop. Well, hello and welcome to the workshop, and today we're going to be working with the LSM303AGR sensor. Now, what does it sense, you might ask? Well, Adafruit, who make the module that we're working with today, just refers to this as a multifunction sensor, so that really doesn't tell you very much. STMicroelectronics makes the actual sensor chip itself, and they refer to it as an eCompass, and that will give you a better idea of what you can do with this sensor. The sensor is actually two sensors in one that can measure acceleration and the other one that can detect magnetic fields in 3 dimensions. And by doing this, we can determine what position we are in. This has a lot of applications in things like robotics, and we can also use it just to build an electronic compass, and we're going to do that today. But first, let's go and take a look at the LSM303AGR. The LSM303AGR is 2 sensors in one, a magnetometer and an accelerometer. The magnetometer measures the strength and direction of magnetic fields. The accelerometer measures acceleration in 3 dimensions. Magnetometers are used to construct compasses. They can also be used for metal detection, and they have a lot of usage within navigation for vehicles and robots. An accelerometer can measure tilt, motion, and vibration. It can be used for step counting. Another use for an accelerometer is for airbag deployment. The magnetometer in the LSM303AGR is the LIS2MDL sensor. It has a range of plus or minus 50 Gauss and a data rate of 10 Hz to 100 Hz. The accelerometer sensor is the LSM303. It has a selectable range of plus or minus 2G to plus or minus 16G. It can also be operated in a low power mode. We'll be using the LSM303AGR on a module from Adafruit, and it has the following pinouts. The Vin is the input voltage, and this can be 3.3 to 5 volts. Vout is a low current 3 voltage output from the internal regulator. GND is of course the ground. The SCL is the I2C clock, and the SDA is the I2C data. And int-M is an interrupt from the magnetometer. There are also 4 pins on the top. CSM is a chip select for the magnetometer. CSA is a chip select for the accelerometer. And IA1 and IA2 are interrupts for the accelerometer. These pins can be left unconnected in most cases. The module also has 2 quick connectors for easy I2C connections. The actual sensor is in the dead center of the module, and you should know this if you need to position it correctly for your readings. You'll also need to know the orientation, and both the x-axis and y-axis are clearly marked on the module. So now let's take a look at the LSM303AGR module. And here we have the LSM303AGR module, and it's a fairly basic module. You can see the sensor itself is right dead center on it, and you can see the X and the Y orientation printed on the module. There are 2 quick connectors. You could use either of them to connect I2C, and you can use the other one to daisy chain another sensor if you wish. Otherwise, I've got the pins soldered on, but they don't come with the pins soldered. Like most Adafruit products, you need to solder the pins on yourself, and so that offers a lot of versatility. Actually, you could even solder them on the other side, or omit soldering these pins on the top here because you're probably not going to use them. On the back of the module, there really isn't very much to see, just basically the writing that tells you what the module is, and that's about it. It also gives you the I2C addresses. So it's a fairly basic looking module, but it does some pretty amazing things. So let's go and see how we can hook it up to a microcontroller and start using it. You could use the LSM303AGR with pretty well any microcontrollers. It supports both 3.3 and 5 volt devices. I'm going to be using it with a Arduino Xiao ESP32S3 board, which is a board I use a lot here in the workshop. We'll connect the 3.3 volt output of the Arduino Xiao to the V-in pin on the LSM303AGR module. The Xiao's ground will be connected to the module's ground. Pin D5 on the Arduino Xiao will be connected to the SCL input on the LSM303AGR. And finally, pin D4 will be connected to the SDA input. And this completes our wiring. So now that we've got our LSM303AGR hooked up, it's time to start working with it. And as this is two sensors in one package, we're going to work with the sensors individually. We're going to start now with the accelerometer. So let's go and learn what an accelerometer is, how it works, and how we can use the accelerometer in the LSM303AGR module. An accelerometer is an instrument that can measure changes in speed or direction of motion. It can detect static forces such as the acceleration of gravity and dynamic forces such as movement and vibration. An accelerometer can determine tilt or orientation by sensing the direction of the gravitational pull. The accelerometer can sense tilt and motion in the X, Y, and Z or Z directions. The accelerometer in our sensor is a MEMS sensor. MEMS is an abbreviation for Micro-Electro-Mechanical-System. It consists of both a moving plate and some fixed plates, and the moving plate is attached to a couple of springs. To operate, the capacitance between the fixed and moving plates is measured. When acceleration is applied, the moving plate will move, and the capacitance between the moving and fixed plates will change. This change of capacitance is used to measure acceleration. The LSM303 accelerometer used in this sensor is a 3-axis MEMS capacitive accelerometer. It has a range that's selectable between plus and minus 2G to plus and minus 16G. Note that G is an abbreviation for the G-force, or acceleration of gravity, which is 9.8 meters per second squared. The device has a 16-bit resolution, and it communicates an I2C address hexadecimal 19. It incorporates free fall, motion, and wake-up detection, and it can be run in normal, high resolution, and in low power modes. To work with this accelerometer, we'll be using the Adafruit LSM303 Excel library, which you can install within the Arduino IDE. So let's get working with our accelerometer. Now you're going to need to install the Adafruit LSM303 Excel library using your library manager, and once you do that, you can run the sample code that comes with it. There's only one bit of sample code, and it's shown here. It's called Excel Sensor, and it tests the accelerometer. Now it starts off by loading the required libraries, the one you just installed, the Adafruit sensor, which is their universal sensor library, which will get installed with this if you don't already have it, and the wired library to talk to I2C. We start off by creating an object to represent our sensor, and here's a function that it starts off with called display sensor details, and it does display all of the sensor details. It creates an object called sensor, and it prints out the sensor's name, its version, its ID, maximum and minimum values, and resolution, etc. So we can call this function up anytime we want to see those parameters. Now we'll go into setup, and here's something that you may have to edit to get this to work with the ESP32. I found that it wouldn't work until I deleted these lines over here for the ESP8266. I'm not sure why it actually went through that, because this isn't an ESP8266, but I'm just mentioning this. If you can't get it to work, try taking these lines out. Otherwise, we're starting the serial monitor. Note that they're running it at 9600, which isn't that common these days, but perfectly fine. Prints out it's an accelerometer test. We initialize the accelerometer, and assuming it initializes, we go and call that function display sensor details to display all the basic functions. Now within the setup, we can set a few things, and you can use these as examples for your own code. Remember, the range has a number of different ranges, and we can set it to a bunch of different ranges with this parameter over here. So right now it's setting it up to this range, but there are other ranges as well. You can do 2 grams, 4 grams, 8 grams, or 16 grams. So you can experiment with this. Another thing thing you can experiment with this is the mode, and we're setting it into normal mode, but you can also set it to low power or higher resolution mode, and again, just following along over here. Once we get out of setup, we go into the loop, and in the loop, we're basically just going to measure the sensor. We're going to create it as an event and get the event, and then we'll display the parameters of it, the acceleration in the X, Y, and Z or Z axis. And that's basically it. We're going to delay for half a second and go back and do it all over again. And so that's the code for testing out our accelerometer. Let's load it up and watch it work. And so we're running our accelerometer demo, and if you look at the serial monitor, you will see that although the board is stationary, we are getting hardly any reading on the X and Y axis because the board is stationary, but the Z axis gets a reading, and the reason for that, of course, is it's measuring the acceleration of gravity, and gravity's acceleration is 9.8 meters per second squared, and this is reading out in meters per second squared. It's reading a little lower than 9.8. I don't know if that's a calibration issue, or if maybe the gravity's off in the workshop. That would explain a lot of things, actually. Now let's move it on one of the axes. I'll move it on the X-axis right now, and you'll notice that the X-axis, when I accelerated, I got some readings there. Now we'll try moving the Y-axis, and I get the same results. And so it does seem to work. So the Accel sensor demo is a pretty easy way of illustrating what happens within the accelerometer. Now, the other component in the LSM303AGR module is the magnetometer, and we're going to work with that next. Now, the magnetometer has been calibrated at the factory. However, that calibration is not going to be entirely perfect. There can be slight variances during the production run. So we also are going to learn how to calibrate our magnetometer. So let's go and see how this works, how to calibrate it, and how to use it. A magnetometer is a sensor that measures the strength and direction of magnetic fields. It can detect the Earth's magnetic field to determine your heading. A magnetometer senses orientation, rotation, and movement relative to the Earth's magnetic field. Now here's a diagram of the Earth's magnetic field. Note that this is not to scale. These 2 points represent the magnetic North Pole and magnetic South Pole, and these are the poles in which your compass will point towards. These lines represent magnetic field lines, and again, these are not to scale, as the Earth's magnetic field actually extends tens of thousands of kilometers, and that's a good thing. It protects us from charged particles from the sun. Note that the magnetic North Pole and magnetic South Pole are not the same as the geographical North and South Pole. This causes compasses to be inaccurate at the far north and far south regions, and you can get a correction factor if you know your longitude and latitude. Once again, this diagram is not to scale, and the deviation is nowhere near as great as I'm illustrating here. There actually were 2 versions of the LSM303 sensor. The LSM303AGR, which is a sensor we're using today, which uses an AMR or anisotropic magnetoresistive sensor, and the LSM303DLHC, which used a Hall effect sensor. The current device is more sensitive than the older device. An AMR sensor is comprised of magnetoresistive elements. These are elements that change resistance when exposed to magnetism. These consist of a non-magnetic layer sandwiched between 2 ferromagnetic layers. The non-magnetic layer is somewhat conductive, and it has low resistance with a magnetic field and high resistance without the magnetic field. In an AMR sensor, 4 of these devices are arranged in what's known as a Wheatstone bridge, which is a configuration that can measure the value of an unknown resistor with 3 fixed value resistors. The magnetoresistive element on the bridge that goes to a lower resistance will indicate the direction and magnitude of the magnetism. The LIS2MDL magnetometer employs 3 of these AMR sensors. They're passed through a multiplexer to an amplifier and then to an analog to digital converter. The output of this is fed into some control logic, which provides the I2C output. The LIS2MDL is a 3-axis MEMS AMR magnetometer. It has a dynamic range of plus or minus 50 Gauss and a 16-bit resolution. It has an I2C address of 1E hexadecimal and a sensitivity of 1.5 milligauss. It also provides a magnetic field detection interrupt, and you can program the level at which this interrupt is triggered. We'll be working with this sensor using the Adafruit LIS2MDL library, which you can find in the library manager of your Arduino IDE. So now let's go and check out our magnetometer. Now, ideally, before you use the magnetometer, you should calibrate it to account for any slight variations that occurred during production. And there are a number of tools you can use to calibrate magnetometers. One popular one is by Paul Stoffergen, and it's called MotionCal. And this is the GitHub page for it here. And on the GitHub page, you'll note there's a link to the PRJC website, to their store, where they actually have some compiled versions. And that's this page over here. If you go down here, you'll see there's compiled versions for Windows, for Linux, and for the Mac. I've got the Windows version, which is actually just an exe file. There's no installation required. You just run the exe. You could even stick it onto a thumb drive or something and take it from machine to machine if you wish. And I've got it over here. This is the motion sensor calibration tool. As you can see, it's got a fairly simple interface. It's not that new a tool. If you look in the help and the about, you'll see it was copyright 2018. But nonetheless, it still works great. What it allows us to do is get these values over here for magnetic offset. And these are values that will plug into our code to allow for little variations in our sensor. And in order to run this, though, you need to be running some code on the sensor that is compatible with this tool. So let's go and take a look at a sketch we can use to run on the SHAO in order to use the motion sensor calibration tool. Now, in order to perform the calibration, you're going to need to run a sketch on the ESP32 with the sensor, and then connect the sensor up to your serial port on your PC, and then use the utility to calibrate it. Now, Adafruit has instructions for using something called Sensor Lab, but I could never get that to work, and it's my understanding the reason may be that I'm using an ESP32, and Sensor Lab apparently doesn't play very nice with ESP32s. So I've got my own calibration sketch up over here, and it basically does the same thing. It outputs a format that's required by the MotionCal utility. And so I've got some instructions here, etc., for using it. And we'll go into the actual code itself. Now, we're going to be loading all of the libraries, the wire library, and both the library for the magnetometer and the accelerometer over here. And the reason is that MotionCal can accept both. So we're going to output both, even though what we're trying to calibrate is just a magnetic sensor. We also use the Adafruit Universal Sensor Library. We create objects for both our accelerometer and our magnetometer over here. And in setup, we go and set everything up. The serial monitor will initialize I2C. We'll initialize the accelerometer over here and initialize the magnetometer down over here. We're also going to configure the ranges on the accelerometer over here and the data rate on the LIS-MDL magnetic sensor. Then we'll go and print a few things up on the serial monitor, including the instructions we need to do, and we'll close it because we aren't going to be running this from the serial monitor. We're going to be using MotionCal and just using this to provide data. And so we're going to go into the loop here right now. Again, we're going to get an event. We're going to read the event for both acceleration and for the magnetometer here. And we're going to convert those to the values that are required by MotionCal. So that's these values over here. And we're also going to send gyroscope values because they are part of the data stream. However, we don't have a gyroscope, so we'll just send out zeros. And we'll do some more conversions for the magnetometer values. And then we're just going to output everything in the format that MotionCal wants on the serial monitor. So basically, we're going to output it on a comma-delimited string. There's a whole bunch of commas over here after we print out the values. We're also going to output this in uni format. MotionCal doesn't use it, but it can use it for debugging, so we'll output this here, and then we'll update the rate. We'll do this 10 times a second, and do it over and over again. So this should create a steady stream of data that MotionCal can use to calibrate our sensor. So let's load it up and give it a try. Okay, I've got my motion sensor calibration tool running under Windows, and I've got my Arduino shell loaded with the code, and it is connected to the USB port like it was for the Arduino IDE. And I've turned off my Arduino IDE, and that's an important thing to do because you don't want the serial monitor on that conflicting with this tool. Now, what we have to do first is pick the port that the shell is connected to, and it's usually fairly obvious. In this case, it's COM11. Of course, yours will be different. And we can start doing the measurements. And what we need to do is just move this board around. And as we do, you'll start seeing these little dots. And notice I'm moving it up, I'm moving it down, I'm moving it in circles, moving it upside down, etc. What we're trying to do is create a sphere in the center over here. And it takes a little while to do this. In fact, it takes probably about 10 or 15 minutes to go through this fully. Now, I should mention that I'm just doing this as a demonstration for you. It actually is probably the worst place that I could possibly do it, right here on my workbench. And that's because you're supposed to do this away from devices that might interfere with it, things that have large bits of ferrous metal. And of course, there's lots of things in the workshop that qualify like that. Also, if you take a look at the back of my solderless breadboard, it does have a metal plate on it. Now, that's aluminum, so I don't know if that's going to really affect the magnetic field, but again, it probably isn't the best thing. Ideally, you'd attach the sensor to a long cable, do it independently, and take a notebook or something outside and do it where you're away from anything that's large and metal, and then you'll get a more accurate calibration. So I'm really doing this as a demo. Now, what you're looking for is not only the sphere, and I've only got the beginning of a sphere over here, it looks, but you're also looking at the bottom over there where you see it says gaps. You want to get that as little as possible. Ideally, you want to get that under about 5%. Now, as I said, this takes a while to do, so I'm going to stop this one now and just show you an image I took of one I did earlier. That's just right down over here, and we'll just bring that up so you can see it a bit better. There you go. And the gaps at the bottom here, I got down to 0.8%, so that's pretty good reading, although again, this was done at my workbench, so I don't know how accurate it is. And here's the magnetic offset, the X, Y, and Z values. And this is what you're doing everything here for. You want to get these values, you can plug it into your code, and that way it'll correct any offset in the sensor, and it'll make your sensor more accurate. Now, the Adafruit LIS2MDL library that we installed earlier has a number of examples with it, and one of them is called Mag Sensor, and it's just something you can use to test a magnetometer. Now, it starts off by loading that library as well as the Universal Sensor library and the wire library. It then goes and sets up an object for the sensor over here, and then a number of definitions which really make no sense whatsoever because these are definitions for the SPI bus, and we're using the I2C bus. However, as we'll see later on, you can modify this to use SPI, at least with a different sensor, not with this one. Okay, we go into setup, and in setup we're going to run the serial monitor, this time at the more common speed of 115/200. We're going to make sure the serial monitor starts. We'll enable the auto range on the device, and we're going to set that to true. That'll make the readings much easier to get. We'll initialize the sensor, and this is where the SPI bus comes in. There are connections down over here for begin SPI, so if you have a sensor that connects with the SPI bus, you can use that. But I want to point out that would be when you have a separate magnetometer sensor, not our combined sensor like we have today, because this sensor doesn't expose the SPI bus. It only exposes the I2C bus, and so this is the correct line. There's no editing required over here. We'll then go and display some basic information on the sensor, and we'll just use one of the built-in functions called print sensor details, and that'll print some details of the sensor out to the screen. Now in the loop, it's pretty easy. Once again, we're going to get a new event, and we're going to assign it to the event and print out the event properties. And so we have the X, Y, and Z axes over here, and we're going to print out the X, Y, and Z values. And you can also, as it shows over here, get the raw values if you would prefer by changing the code over here or by unremarking these lines. We put in a short delay and then we do it over again. So again, a pretty simple example. The library is doing most of the work for you. Let's load it up and take a look and make sure our magnetometer is working. Okay, so we have our magnetometer demo running, and you can see the X, Y, and Z axis and the amount of magnetism it is picking up on each. Now, if I turn the board, you'll notice that the X and Y values tend to change, and that, of course, is because of the Earth's magnetic field. The Z value remains relatively constant. But one way to really see this thing work is just to bring a magnet near it. So I've got this tool with a magnet on the end of it, and look at the display right now when the magnet comes near it. Now move the magnet away, and the display goes back to where it was. So it's definitely capable of picking up magnetism. It's a very sensitive sensor, and it's a great display of the magnetometer. Okay, now that we've seen how our magnetometer works, it's time to use it to build a compass. And we're actually going to work on two different compasses. The first one is a very simple one that we're just going to use a sample sketch for. This is a compass that just outputs on the serial monitor, and this is the sort of code you would use for, say, robotics, where you're trying to just give the directional coordinates to a robot. You don't really need to see a compass dial or anything. We'll go on after that to build a compass with a dial, but first of all, let's go and use our sensor to build a very simple compass. Now, to build our simple compass, we'll just use one of the example sketches from the LISMDL library, and this one is called Compass. And it starts off by including the libraries we require: the wire library for I2C, the Adafruit Universal Sensor Library, and the library for the actual magnetometer over here. After that, we define an object to represent the magnetometer, and we go into our setup. We set up the serial monitor, and we initialize the magnetometer. In the loop, we'll go and get a sensor event, and we'll assign the sensor event. We'll also define a constant for pi over here, and then we'll use that to calculate the angle, and this is how the angle is calculated. We're calculating an angle from 0 to 360 degrees, and we're going to normalize that to 0 to 360 over here, and then we're just going to print it. So it's really a fairly basic sketch. Again, a lot of the work is done in the library. Let's load it up and see our simple compass work. And you can see the output of the simple compass demo on our screen. It just gives you the compass heading. So as I turn the board, you'll see that heading change. And we're approaching 360 degrees over here. So there we go. After going to 360, we go back to 0, 1, etc. So that means it is pointing north. And let's go in the other direction for a bit. And so there you go. It's a very simple compass. It just gives you the heading. But if you're using something like robotics or something like that, where you just need to get a heading, that's pretty well the only value that you'll need to get. So the simple compass demo shows you a very easy way to turn this sensor into a compass. So now that we've built a very simple compass with the serial monitor, let's move on and make an actual compass that has a compass display. Now what we're going to do is add an OLED display to the circuit that we already have and use it to display a compass dial. Now admittedly, an OLED display is a pretty small display, so this is going to give you a pretty tiny compass, but you can use this same principle with another display, say a larger LCD display, and use it to build a really functional instrument. If you do that, make certain to mount your sensor so that it's in the center of the compass display, right below it. Otherwise, it won't really make a lot of sense. At any rate, let's go and see how we hook up an OLED to our circuit and use it to display a compass. We're going to take our existing circuit and connect an OLED display. Our OLED will be a standard SSD 1306 OLED. We'll begin by connecting the 3.3 volt output of the Arduino Xiao to the VCC pin on the OLED display. Note that you could also drive the OLED with 5 volts and it will still work. The ground from the Xiao will be connected to the OLED display's ground. Pin D5 of the Arduino Xiao will be connected to the SCL or clock line on the OLED display. And the data or SDA line will be connected to Xiao's pin D4. And that's it for the wiring. Now let's go and take a look at some code we can use to display a compass on our OLED display. Now here's a sketch that we're going to be using for our OLED compass, and remember you can download this sketch from the article that accompanies this video on the DronebotWorkshop.com website. Now we're going to go and start the sketch by including a number of different libraries. We're giving it everything here: the wire library for I2C, the libraries for both our accelerometer and for our magnetometer, because we're also going to use the accelerometer within our calculations, because a real compass, when you move around, is affected by it. So we're going to do that as well. The universal sensor library, and the GFX and SSD 1306 libraries, which are used for the display. We define a number of display parameters over here, including the address of our display at hexadecimal 3C. So if you've got an OLED that has a different address, you need to change that. We'll set up objects for both the accelerometer, the magnetometer, and the display. And here is where you would insert all those offsets that you got if you calibrated your magnetometer. So insert them over here if you have those values. We're actually not using the Z value, but the X and Y value do come into play. Then we define a couple of constants for the compass: the center, X, the radius, and the needle length. And we'll go into our setup. In setup, we start our serial monitor, initialize I2C. We'll initialize the OLED display. We'll clear the display and set the cursor and everything. Then we'll go and initialize the accelerometer, and we'll initialize the magnetometer. And then we're going to set the range on the accelerometer as well as the data rate on the magnetometer down here. We'll clear our display, we'll print out ready, and then we'll print out a message saying that you should calibrate it with a figure 8 move, because that's how you do calibrate the magnetometer, by moving it around in sort of a figure 8 at the beginning. We'll delay for 2 seconds so that message stays on the display. Now before we go into the loop, I want to show you a few functions that are down here at the end. So let's go past the loop for a bit. Get cardinal direction. We're going to pass it the heading, and we're going to print out the cardinal direction. So the heading is basically north, north, northeast, northeast, east, northeast, etc., etc. And so we're going to return that string. On draw cardinal markers, we are going to draw the direction labels. So these are the labels for north, south, east, and west that are just being drawn on our compass. And if you decide to change the size, or if you're using a different size display, you can mess around with these numbers to put them in the correct place. We're also going to draw a number of tick marks, and that's for the intermediate direction. So we'll do that over here. Now here we do draw a compass needle, and it draws the needle for the compass. And we're also going to place the heading so we know which direction to place the compass needle in. And so we're going to go and get that direction over here. We're going to compute the needle length, the needle width, etc. We're going to draw the north needle over here, and this is just a bunch of parameters that we're going to give the OLED. We're drawing the south needle and the arrowhead on the north end of the needle. And so now that we've seen those functions, let's go back up to our loop. And here it is. And so once again, we're going to get events for both the accelerometer and the magnetometer. And we're going to apply our offsets over here to the magnetometer events. So if you have offsets on the X and Y axis, they'll be applied over here. Then we're going to calculate the heading using these. And we'll make sure the heading never goes below 0. If it does, it's 360 degrees. Now, we're going to get the direction by doing the get cardinal direction. So we'll just print that string. That's the one that prints north, northeast, etc., etc. Then we'll go to the display and we'll clear it, and we'll print out the heading, and we'll print out the direction on the top so that you can see that on the top. And then we draw the circle, which is actually the circle for the compass. We put the cardinal markers. We place our needle in the right direction of the compass, and we'll fill that circle. We'll display that, and we'll delay for 1/10 of a second and go back and do it over again, so our compass is fairly responsive. So let's load this up and take a look at our compass working with an OLED display. And here we have our LSM303AGR compass on the OLED display, and as you can see, it's pointing northwest right now, giving both the heading and the direction. And as I move it, you'll see that the pointer moves with it. We can get it sideways here. It'll be going north. And we get it more to this side. It's going west. Now, remember that the sensor itself is actually beside the display, so that's not actually the proper orientation. If you're going to build this as a permanent project, you would want to place the display directly above the center, with the center of the display centered right on the sensor, and then it'll be more accurate. And of course, a larger display like an LCD would probably make it a more practical project, but it does go to show you just how easily we can use this sensor to build compasses with. Well, that about wraps up our look at the LSM303AGR Multifunction Sensor, or eCompass, depending upon who you ask. We've used it to build a compass so you can find out where you're going. And if you need some more information about the sensor, you can just go over to the dronebotworkshop.com website, where there's an article that accompanies this video, and you'll find the link to that right below the video. While you're on the website, if you haven't yet, please consider signing up for my newsletter. It's not a sales letter by any means. It's just my way of letting you know what goes on here in the workshop, and also giving you the occasional preview of my videos, and it's free to sign up for the newsletter. It's also free to sign up for the DroneBot Workshop forum, where you can talk electronics with a number of like-minded individuals who can help you with your project, or maybe you can give them a hand. And the forum is, as I said, free to sign up for. And while you're in that signing up mood, if you haven't yet, please consider subscribing to this YouTube channel. I make videos about electronics and microcontrollers and artificial intelligence, and if you like this video, I think you'll like my other ones as well. Signing up is really easy to do. All you need to do is to hit that red subscribe button and also click on the bell notification, and if you do that, you'll get notified every time that I make a new video. So until I make a new video and we meet again, please take care of yourself, stay safe out there, and I'll see you soon here in the DroneBot Workshop. Goodbye for now.